Hello, good morning. This is Dr. Senthil Kumaran, Assistant Professor, Department of Electronics and Communication Engineering, Tyagarajar College of Engineering, Madurai. Today, now we will see about maximum a posteriori probability map. Let me first explain about the difference between maximum likelihood and maximum a posteriori probability. In maximum likelihood, the prior probabilities, what we will see is we will assume that it is of equiprobable. But in case of maximum a posteriori probability, the source probabilities will not be equiprobable and it will have different probabilities of occurrence. That is, here in maximum a posteriori probability, the Bayes rule models by learning from experience. That is, from the experience we will be having some clues, and with the clues we will be deciding that the incoming signal will be in favor of which type of sequence. In the natural world, our prediction is influenced by our prior beliefs. Map estimation takes our prior beliefs into account, whereas MLE does not. Maximum a posteriori probability pulls the prediction towards the prior to an extent that depends on the strength of the prior. Map is closer to our natural style of prediction. It takes our bias into account. So, if these experiments, if we go for n times and that n tends to infinite, this map will tends to look like MLE, that is asymptotically as n tends to infinite. And let me ask the reflection spot question, that is distinguish between maximum likelihood and maximum a posteriori probability. So what you have to think is you have to think for a moment and then you have to answer. So now I will give you a pause. Then I will resume and I will tell the distinguish between maximum likelihood and maximum a posteriori probability. Pause. Yes, well, you would have think of the difference between this maximum likelihood and maximum a posteriori probability. Let me tell the answer for that one. That is, in maximum likelihood, we will be having this source probabilities, what I told you earlier, is of equiprobable in nature. But in case of map, we won't use this as equiprobable. The probabilities will be different. That is, it may be, for example, if you use two sequences, the one will be the probability, for example, 0.6, the other will be of 0.4. Okay. So what we will do is we will take this prior probabilities into account, and then we will decide what signal we will be receiving. That is, for example, in case of earthquake, for example, in a particular region, every 10 to 15 years we have an earthquake, that is with a slight tremor, and for every 300 years in that region if we have a massive earthquake. So we can able to decide that the earthquake will be in near future or it will be in far. So because of these number of experiments already it has been occurred, so with that we can able to decide that. So for example, 15 years back a tremor has been occurred in the particular area, so definitely at the near future there will be a slight tremor. Or else if 300 years for 300 years if there is there has been not a big earthquake, definitely the big tremor, big earthquake will be in near future. So like that, by using these past experiments from the from the experiments we'll be taking these clues. If we take these clues and if we use in our experiment, then we can decide at what situation, at what time the earthquake will come. So like that, here what we'll be doing is, that is, again I'll be repeating this one. Map puts the prediction towards the prior to an extent that depends on the strength of the prior. Map is closer to our natural state of prediction. It takes our bias into account. Okay. Let me explain how to find the decision boundary by using this maximum a posteriori probability. We have these two symbol sequences x1 and x2, and we have this condition probability with this density function f of y given x2 with p of x2. This p of x2 is the probability of occurrence of this sequence, and this p of x1 is the probability of occurrence of the sequence, but here in these cases this won't be equiprobable. Now with this case, now we have to find this decision boundary. So what we are doing is we are using this density function, this probability distribution function, this PDF, There is 1 by root 2 by sigma e to the power minus y minus x1 the whole square by 2 sigma square into p of x1, and equating it to the other one. And why we are doing this is we have to find this decision boundary y. So we will be simplifying this expression, taking log on both sides, and after simplifying, finally we'll be getting this term y is equal to sigma square by x1 minus x2 ln of mod p of x2 by p of x1 plus x2 by 2. And from this expression, what we understand is this will be the exact decision boundary, but due to the probability of occurrence of these symbols are not equiprobable, this decision boundary will be shifting towards right or left according to these probabilities of occurrence of the sequence. So with this expression, now we will be finding the decision boundary y. Okay, we will see one example. We will see one example problem. With that we will easily understand that how this decision boundary is shifted up, and how we can able to design the sequence in favor of that is, we have to design in favor of each sequence. Consider a random variable x belongs to -3, -1, +1 and +3. That is, in this case, for example, we assume that it is in 4PAM with a priori probabilities. For +or -3 it is 0.1 the probability of occurrence, and for +or -1 the probability of occurrence is 0.4. And we can note that these probability of occurrence are not equiprobable. If in this case, if it is of equiprobable, we will have 0.25, 0.25, 0.25, 0.25, but here it is not the case. Given an observation of the random variable y is equal to x plus n, where n is a zero mean Gaussian random variable with variance sigma square independent of x, find the decision regions for a map detector. Now suppose sigma square is equal to 0.25 and y is equal to 0.1. What is the decision? So now what we will do is we will plot as these functions -3, -1, +1 and +3, and if at the receiver side if it is x cap, that is with noise x1 plus n, we will be deciding in favor of x cap, that is -3, and if x2 means it is -1, x3 is +1 and x4 is +3. So like this we will be drawing these densities here, and now we will be saying we have to find the threshold regions now. For case 1, at the overlapping point of y1, so we take these densities at -3 and -1, and in these expressions already what we have derived the decision boundary. So we substitute this -3 and -1 here, and now we know that for -3 the probability is 0.1, and for -1 the probability is 0.4. That is, these probabilities are different now in this case. So if we find for this, we will be getting the decision boundary at -2.173, but in the real case, that is in normal, if we do with respect to maximum likelihood, we will be getting the decision at -2, but now we will be getting the decision at -2.1733. And now in case 2, what we will be doing is we will be finding the decision region at y2, and obviously we can see that these signals now here is -1 plus 1. So for these signals now we will substitute here -1 plus 1, and here we can note that for -1 plus 1 the probabilities are 0.4, and we can note that if we substitute both in numerator denominator 0.4, this value will become 0, and exactly we will get at 0. So this decision boundary will be at y2 is equal to 0. And for the case 3, what we have to find is we have to find the decision region y3 with respect to these signals 1 and 3. So you substitute this 1 and 3 symbols in this equation with these probabilities. Now the decision region will be shifting towards 2.1733, but in real case, but in case of maximum likelihood, it will be at 2. But now if these probabilities are different, now we will be having the decision region at 2.1733. The conclusion is, in the question it has been asked that if the received signal is 2.1, we have to decide in favor of +3 or +1. But in this problem we have found that decision region is 2.1733, but now the incoming signal is 2.1, that is, it is less than this 2.1733. So this 2.1 lies the left of this decision region, so we have to decide in favor of +1. But in case of a maximum likelihood, we can tell that if it is 2.1, we have to favor in case of 3. But since the source probabilities are not equiprobable, in this scenario, we should not decide in favor of +3. We should favor in case of +1. So that is what here it has been explained. Even though if the received signal is at 2.1 as given in the question, the decision will not be in favor of +3. In this problem, with the source probabilities the probability of plus or minus 3 is 0.1 and probability of plus or minus 1 is 0.4. We obtain the decision regions as minus 2.1733, 0 and plus 2.1733. The received signal plus 2.1 is now at the region y2 and y3, and this corresponds to the signal component plus 1. Hence the decision will be in favor of plus 1. So hope so that you would have understood the concept behind this maximum a posteriori probability. So in this section what we have seen is initially I have posted under this reflection spot question, that is distinguish between maximum likelihood and maximum a posteriori probability, and also we have to find that in the doing activity, what we have to do is we have to derive this expression and we have to find this decision boundary y, and the question may be different. If the signal is 2, what will be the decision we have to take, or if the decision is 2.5, what decision we have to take. So those problems the students has to work with that, and they have to find the decision, they have to take the decision, and we have to decide that it will be in favor of which symbol sequences. Thank you. Hope you have understood about maximum a posteriori probability. Thank you.